Okay, so this is a set of notes on pie charts, frequency polygons, ogives, and graphs that deceive. A lot of going on here. It's just kind of an odds and ends section. So let's get started. A pie chart is something that you've probably seen before. Basically, you take a circle. You have categorical data. So let's say we used the example we did a little while back where you have like cartoons by Disney, cartoons by MGM, cartoons by Warner Brothers, cartoons by Universal, and cartoons by 20th Century Fox. And then like we kind of assigned them each a color. So like Disney may have the largest piece of the pie, and then MGM might have another piece of the pie here. Ooh, that was really bad. Let's do that a little better. There you go. MGM might have another piece of the pie here. And Warner Brothers might have another little piece here. So that might be the Warner Brothers section. And Universal might have their piece of the pie. And finally, 20th Century Fox might have what's left over. Now, ideally, this is the center of the circle, and these are all like wedges of that circle, and these things are proportional to the size that each of these companies has. Now, essentially, this does the same thing that the Pareto chart did the other day, and in fact, the preferred way of looking at this data is the Pareto chart because it does seem to give people a little bit more accurate envisionment, but it's not uncommon for publications to use pie charts, more or less just because they're attractive and fairly easy for people to grasp and understand what's going on. Okay, so we're going to move into the idea of a frequency polygon. Okay, so to understand a frequency polygon, we're going to go back and use a frequency distribution. And we had a frequency distribution of IQ scores at one point that we were working with, where we had a bunch of classes, like 50 to 59, there were 2 people. Sorry, 50 to 69, there were 2 people. 70 to 89, there were 33 people. From 90 to 109, there were 35 people. From 110 to 129, there were 7 people. And then from like 130 to 149, there was 1 person. So this gave us the distribution. So all we're going to do here is we're going to look at the midpoint of each of these classes. So the midpoint of this one would be 59.5. The midpoint of this one would be 79.5. Of this one would be 99.5. Of this one would be 119.5. And of this one would be 139.5. And we're going to build a little graph using those midpoints. So along the bottom of the graph, we're going to have those midpoints. 59.5, 79.5, 99.5, 119.5, 139.5. We might extend it a little bit further. We might drop down here to like 39.5 and up here to 159.5. And then we're going to put in dots that represent those frequencies. So like at 39.5, there's 0. We've got like 2 here. And then we jump up to like 33, then 35, back down to 7, down to 1, and when we get down to 159.5, we're back down to 0. So if I connect those dots, I now get a polygon. And that polygon is what we're going to call a frequency polygon. Now, the nice thing about this is it gives me a pretty good idea of like the shape of the data. Now, it's got the same general effect that a histogram would get. You get it kind of quickly. This is a fairly bell-shaped set of data. It looks a little bit skewed right. So you get that idea kind of quickly and without a whole lot of effort. So that is what we're going to call a frequency polygon. Okay, so we got a couple more sections of the notes here. Not too bad. We got through 2. We've looked at pie charts. We've looked at what a frequency polygon is. Now we're going to look at something called an ogive. Okay, so an ogive is spelled O-G-I-V-E. It's pronounced ogive. All right, so this can also be called a cumulative frequency polygon. Let's look again at our frequency polygon. We had 50 to 69. We had 2 people. From 70 to 89, we had 33 people. From 90 to 109, we had 35 people. From 110 to 129, we had 7. And from 130 to 149, we had 1. Okay, what we're going to look at is the breakpoints here. Okay, so the breakpoint here is going to be 49.5. This one is 69.5. This one is 89.5. We have 109.5, 129.5. And if I made another one up here, it would be 149.5. And we want to look at how many people are less than that breakpoint. So here there's 2. Here, less than this breakpoint is 35. Less than this breakpoint is 70. Less than this breakpoint is 77. Finally, 78. So when you build the ogive, you're talking about cumulations. So we're going to put those numbers in here. 49.5, 69.5, 89.5, 109.5, 129.5, and 149.5. Okay, so here we've accumulated 0 at that point, 2 here. We jump up to having 35 here, and then 70 here, and then 77 here, and then 78 there. And if you connect these, you get a sense that because it's cumulative, this value is always increasing, but you get an idea of how fast it's increasing during which spans. So like the fastest rate of increase is between 69.5 and 109.5. So you get an idea of, as you keep ratcheting up the one value for the IQ scores, how much more of the population is being added from one band of IQ scores to the next. This is what we call an ogive, and it's not a very frequently used graph, but it is fairly useful to show you like the rate at which you are accumulating growth as you raise scores or values. Okay, so sometimes graphs can be deceptive. Graphs that deceive. And we want to look at 2 common ways that this is done, and like how it works and why it works. We should probably fix that. Let's make that deceive. There we go. DECEIVE. There we go. That's a little better. All right, so graphs that deceive. One way that we can do this is by building graphs that don't have a vertical 0. So if they have no vertical 0. So here's what's going on. It's like you have like a graph, okay, and you're doing maybe like a bar graph, and you start like this at 9100. Okay, and this guy looks tiny, and this guy looks a little bigger, and this guy looks bigger yet, and this guy looks even bigger. Okay, but had I actually started this graph out at 0, those differences are not going to be so great. And by making the graph only like the top portion of it, which would be like 9100 up here, it overemphasizes the difference between these bars when realistically it's probably a uniform distribution. So you got to watch when you're looking at your y-axis, what is the number that's being represented here? If it's not 0, then chances are there's maybe some trickery going on here, and you need to be cautious with that graph. So the y-axis should always start at 0. The x-axis doesn't have to, but the y should always start at 0. The other common thing that people can do when they're making graphs that deceive is oftentimes happens in a pictograph. Okay, and like you've got a little picture here, and then we want to say like something tripled in size, so like 1, to 2, to 3. So we make another picture here, and this is deceptive because this ball here is not 3 times the size of this ball, but it's in fact 9 times the size. Like if it were 3 times the size, the picture would look like this. There's 1, 2, 3 times the size. That's 3 times the size of this. But if you look at this guy, right, and you say, oh, wait, that's 3 times the size, but that's 3 more times the size, and that makes that ball actually look like 1, 2, 3, 4, 5, 6, 7, 8, 9 times the size, when in fact it's supposed to only represent something that is times 3. Okay, so this is an accurate representation of 3 times the size. This is not. Okay, so what we'll call this is scaling 2 dimensions of the graph. Okay, you can either scale its height or you can scale its width, but if you scale both, then you're making the graph seem much, much larger than it is. So this is 2 common ways that people create graphs that either deceive or mislead the viewer, and we want to be cautious about those types of graphs. All right, so that's our notes for today. Thank you.